Hi, my name is Henrik Schneider and I'm working on sub-project B4. Our goal here is to improve our understanding of the physiochemical processes in solid fuel combustion under oxy-flame conditions. With physiochemical processes, we mean the interaction of the gas phase, the solid fuel particles and chemical reactions occurring in solid fuel combustion. To know what's really going on in the early phase of combustion, we designed a special combustion chamber, which is right here. This combustion chamber provides optical access to all regions of the flame for the implementation of laser diagnostics. This is very unique because in most combustion chambers no optical access or only little optical access, like you see here on the right, is given. The disadvantage of this is the heat loss through radiation. So we first ignite here a methane flame into which we feed solid fuel particles in a second step. Thereby, we split the thermal power into half. Half of the power is provided by methane and the other half by solid fuels. This way, we obtain up to 60 kilowatts of thermal power in this test bench. To get closer to real conditions, we use the same burner head as here in subproject C1, where no gas assistant is required, but possible investigations are reduced to reduced optical access. The burner itself is swirl stabilized. Here, the gas-assisted solid fuel combustion flame is shown. The swirled secondary flow leads to an inner recirculation zone which transports hot exhaust gas back to the nozzle, as you can see in this scheme. In this high-speed video, particle luminosity is recorded, and particles which are transported upwards are visible in the center, where the recirculation zone is established. Also, the swirl is clearly visible. In B4, we use different laser-optical measurement methods to investigate the solid fuel combustion. The big advantage of these measurement techniques is their non-intrusive character and the high temporal and spatial resolution. By non-intrusive, we mean that we don't influence the measurement process itself during our measurements, like we do when we insert measurement probes into the flame. To give you one example, we use particle image velocimetry, or short PIV, to investigate the flow field and flow field sensitivities on parameters like the type of solid fuel, the thermal load, the atmosphere where the solid fuel is burned, or the particle size distribution. In this video, you can see the gaseous flame and a laser sheet formed in the central plane at the top of the combustion chamber. With the onset of solid fuel feeding, scattering of small particles within the laser sheet is visible. This is how our raw and processed data look like. After applying cross-correlation algorithms on the images to calculate the pixel shifts between two frames, the velocity components within the plane of the laser sheet are accessible. On the right side, you can see the results we obtained from these measurements. For normal PIV, we use very small particles in the order of 1 micrometer. Since we have already lots of particles inside this process, we just use the solid fuel particles for PIV processing. With some pre-processing of the raw image data, we can divide between small particles, which follow the gaseous flow instantaneously, and large particles, which do not follow the gaseous flow instantaneously, to estimate in a further step slip velocities between these two phases. Besides PIV, we also use other laser diagnostics, like coherent anti-Stokes Raman spectroscopy to determine gas phase temperatures. In addition, we investigate particle temperatures, residence times, pollution formation, species concentrations, and much more. All the data and knowledge we gained from this experiment is transferred to other subprojects like C2 and B3 as the basis for development of improved models and for validation data. Experiments like this are necessary to predict oxy-fuel combustion in future.